Okay, here is an example of an important equivalence relation that we will be using. So let's let phi from G to H be a group homomorphism, although a group morphism. This will work whenever whenever phi is any function from one set to another set. This doesn't really have to be groups, but we'll be thinking about it in terms of group morphisms. And so what we want to do is we want to say, we want to take sets, consider the sets S, which is in G, actually H, G, such that phi of S equals H. So, okay, so this, let's call it, let's give it a name, which is SH. So this really depends. So we're picking an element out of H, this one right here, and then we're saying find me all of the people from G which map to H. So the first observation is if H equals 1, then SH is just the kernel of phi, because this is just the definition of the kernel. And then whether or not H is 1, we have the notation. We write phi inverse of H equals SH, which is equal to this thing. And so phi inverse of H, this is called the inverse image. And in fact, if phi is a bijection, and since phi is a group homomorphism, that would make it an isomorphism, but that doesn't matter because we don't even care that these sets are groups yet. But if phi is a bijection, phi inverse will be an actual function. And SH will contain exactly one element. Phi inverse then just becomes the inverse function. But in general, basically in any other case, phi inverse is not a function. So that's something you have to be careful about, because this notation makes it look like a function. But it's really not a function. It's really the inverse image is what it is. Okay, so now what we'll have to say, and the reason this is an example of an equivalence relation is because we can see that because phi is a function, that means that it means that every value in G can maps to something. So that's the same thing as saying SH, the union of SH equals G. And also because it's a function, you know, one value in G can't map to two different values in H. That's, you know, that's sort of analogous to the vertical line test that we would do in algebra or calculus. And so SH are disjoint. So SH partition G. And so by the equivalence of equivalence relations and partitions, we have an equivalence relation. In particular, for A and B in G, A is equivalent to B if and only if phi of A equals phi of B.